Hey guys, it's me, Mr. Ferreter, and let's talk today a little bit about how we classify matter, if that makes sense to you. Now, what's good news is that this is review of content that you learned when you were in 6th grade, so none of this should be particularly new to you, which is good news. But we're going to go over it anyways, just to be sure that you have a refresher, so that you understand how this stuff works as we begin our chemistry unit. So, the first thing that I want you to know is that the smallest building block of all matter is called an atom. Atoms are so small that we can't see them with the naked eye. In fact, we're just starting to develop the technology to be able to see them with microscopes too, which is really hard to believe. If you think about all we've done with technology over the last several hundred years, the fact that we still can't see atoms all that well is pretty remarkable. Someday, I think that we'll have developments that allow us to see those atoms in a lot better shape, which is cool. Now, an atom has a very basic structure. There's a nucleus, which sits in the center of the atom, and that nucleus is filled with both protons and neutrons. Protons are positively charged particles, and neutrons have a neutral charge. And that's kind of really important to understand. So protons, if they're all positively charged, if they sat in the nucleus by themselves, they would repel each other, just like the positive ends of a magnet does as well. And so to prevent them from, or one of the things that prevents them from repelling each other and sort of exploding that nucleus from the inside out, are those neutral neutrons. They sort of act like buffers between the positive protons. That's cool, right? And then surrounding the nucleus are the electrons of an individual atom, and those are negatively charged. Now, most of the time when we draw pictures of atoms, we draw pictures of the electrons in these things that are called electron shells. You can see what they look like here. In fact, if you went to Google right now and you typed in, show me a picture of a nitrogen atom or show me a picture of a cobalt atom, most of the time you're going to see drawings that look like this. And these drawings are helpful for understanding how the electrons work, but they're not particularly accurate either. Scientists now think that electrons exist in what are called electron clouds, which are randomly moving, bits around the outside of the nucleus. So the electrons don't really move in these perfectly neat circles that you see drawn on this particular drawing. We still use drawings like this because they're helpful for understanding how the electrons work, but I want you to know that in reality, scientists now believe that the electrons are moving in these unpredictable cloud patterns around the nucleus instead. Now, one of the core points whenever you're talking about classifying matter is the term elements. Odds are you've heard the term element before. An element is what we describe as a pure substance. And what that means is it's only got one type of atoms inside of it. So if you look at the diagram that's on your screen over here, helium is made up of just helium atoms. There's no other type of element inside of helium except for helium atoms. And the same thing with oxygen. Pure oxygen only has oxygen molecules inside of it. And what that means is, if you have pure oxygen, you really can't break it down into simpler substances. If you broke apart pure oxygen, you're really going to just have still oxygen on your hands because there aren't any other atoms of any other type inside of a pure substance of an element. Does that make sense to you? There are over 100 elements, and they make up all of the substances on Earth. I like to call the elements, the pantry of the universe. And the reason for that is because there's 100 pure substances on Earth, they oftentimes will combine with each other to make brand new substances. And when atoms of elements combine with one another to make a new substance, we call that a compound. We're going to look at that next. So we talked on the previous slide about the idea that an element is a pure substance. It's only got atoms of one particular type inside of it. And on Earth, we have a little bit over 100 elements, and they form the pantry of the universe. Now, you know, this isn't a surprise to you. You know that there are more than 100 elements or substances on the earth. Well, the way that happens is sometimes elements will combine together with one another to make a new substance, and we call that a compound. And there's a really simple diagram of a compound that you know about on your screen right now. This is water, and water is a compound. It's got 2 hydrogen atoms, and it's got 1 oxygen atom, right? H2O, you've heard of that before. Now, here's what's neat about compounds. When elements join together into compounds, they lose their initial properties because they become a brand new substance. So whatever the boiling point of hydrogen was, it's different from the boiling point of water, even though hydrogen is inside of water. Whatever the freezing point of hydrogen was, it's different from the freezing point of water, and even though hydrogen is inside of water. And the reason for that is when those two substances join together chemically to become a compound, they lose their original properties and they gain new properties because they're a brand new substance. Does that make sense to you? Now, there's another type of combination of substances that's called a mixture. Now, a mixture is different from a compound because in a mixture, we physically stir things together, but they don't join together with one another chemically. So when you make a mixture, more than one substance is combined together, but they're not combined together chemically, they're combined together physically. They're stirred together, not joined together with one another. And the reason that's important is because when you're talking about a mixture, you can also separate out those individual substances physically. So if we filter carefully, we can separate the individual substances that make up a mixture back into their individual piles. Or if we sift carefully, we can sift out the individual substances that make up the mixture and separate them into individual piles. So a mixture doesn't result in the formation of a brand new substance with its own properties. You still have two individual substances, they just happen to be stirred together with one another. Now, there are two different kinds of mixtures out there. One type of mixture we call a heterogeneous mixture, and the other we call a homogeneous mixture. And they're easy to pick out. A heterogeneous mixture is a mixture that is not well stirred. It's not uniformly stirred with one another. And what that means is when you look at a heterogeneous mixture, you can see all of the individual pieces and parts inside of the mixture standing alone as individuals. Now, in a homogeneous mixture, it's the two individual substances, or three, depending on how many substances are in the mixture, are uniformly stirred. And when they're uniformly stirred with one another, what that means is you really can't tell where one substance ends and the next substance begins. So you can see a few examples on your screen right now. Cereal with milk is an example of a heterogeneous mixture. They're stirred together, but not so well stirred together that you can't tell where the cereal ends and the milk begins. It's easy to pick out the cereal in a bowl of cereal, and it's easy to pick out the milk within a bowl of cereal. In a homogeneous mixture, one of the examples you see up here is salt water. We did that when you were in 6th grade. When you take salt, put it inside of water, and stir it really well, it becomes clear you can't really tell where the salt is and where the water is. They still exist as separate substances. The salt is still salt and the water is still water. You can separate the salt from the water in salt water by allowing the water to evaporate. However, when you're just looking at it, you can't really tell the difference between where the salt ends and where the water begins. We call that a homogeneous mixture. Now, here's an idea that I'm sure that you probably remember from 6th grade. The atoms inside of solids and liquids and gases are arranged differently from one another. Inside of a solid, the atoms are locked closely together in a rigid pattern. And they move constantly. They're always vibrating, but they don't ever leave their position. That's why a solid from day to day to day looks the same. You walk outside, your car's a solid, right? And it looks the same day after day after day, right? Well, that's because the atoms are locked in a fixed and rigid and unchanging pattern. So you're not able to see them, your car's look change from day to day. In a liquid, the molecules move a little bit faster, and they also can rotate and slide past one another. So there's still some connection between them. They don't just go randomly off into space when you pour your Diet Coke into a cup or your orange juice into a cup. However, those atoms really can rotate and slide past one another, which allows them to change their shape. If you poured a liquid into a different shaped container, it takes the shape of the container. And that's because the atoms are able to rotate and slide past one another. They're not locked in a fixed and rigid position. And then the very last type of solid is a gas, and gases move independently from one another, or the atoms inside of a gas move independently from one another. If we allowed these atoms of this gas inside this balloon, if we allowed them to leave the balloon, they would move unpredictably and they'd go anywhere that they wanted. And that's why it's difficult to hold gas in a particular shape. You got to put it inside of a container to pull that off. Or I should say, more importantly, you got to put it inside of a closed container to hold them in a rigid and unchanging shape. The other thing that's worth knowing is that as you add heat to a solid, a liquid, or a gas, what you're really doing is you're adding energy. You're causing the molecules to move faster. Okay, and you can see that down here on the bottom of this screen. You've got two graphs. Adding heat means adding energy, causing the molecules to move faster. And so I always like to say that a thermometer really isn't a thermometer, it's a speedometer. You're measuring the speed of molecules. And when the temperature of something moves up, what's really happening is the atoms inside of that substance are moving faster from one another. What that means is to change something from a solid to a liquid or from a liquid to a gas, you add heat. And to change something from a gas back to a liquid or a liquid back to a solid, you take away heat. Okay, two last ideas for you. The next is what a solution is. We studied this in 6th grade, shouldn't be new to you. A solution is a homogeneous mixture of two or more substances. And the way it works is you take a solute, which is a substance that is going to be dissolved. Sorry about the light going off. It's a little creepy. And then you put it inside of a solvent, which is a substance that will do the dissolving for you. Oftentimes it's water because, remember, water is the universal solvent. And when you stir those things together, when you mix them evenly with each other, you end up with a solution. Again, this is a mixture, meaning that the solute and the solvent are still separate from each other. They're just really well mixed together. Now, solutions have an interesting property that we like to study in our chemistry unit called the pH of a solution. So the pH is determining how acidic or basic a solution might be. Okay, acids and bases are different from each other. And the scale that we use to determine the pH of a solution runs from 0 through 14. And something that is neutral, so not an acid or a base, is a 7 on the pH scale. Anything below 7 on the pH scale is acidic, and anything above 7 on the pH scale is what's called basic. Now, how do we determine the pH of something? Well, it's in the third bullet on your screen. We determine the pH of something by using what are called indicators. An indicator will react to an acid or a base by changing colors. If I show you a pH scale, if you use an indicator inside of an acid, the more red that the indicator turns up, the more acidic your substance is. And the more green, blue, or purple that your substance turns up, the more basic it is. So we use indicators to determine the pH of an individual substance. Here's a final graphic that shows you some common materials that you may have experienced in your life, and it shows you where that particular substance falls on the pH scale. So milk is pretty close to neutral, right? Because 7 is neutral on the pH scale. But if you look all the way down here, if you're talking about vinegar, or if you're talking about lemon juice, that's very acidic on the pH scale. And then if you look all the way over on this side, soap and ammonia are very basic on the pH scale. So that's how we determine the pH of an individual substance. By the way, if you remember back in our water unit, we measure the pH of water because it's a water quality indicator. And one of the things that pH does is it amplifies the properties of something. So if you've got water that is high in pH, it's going to amplify the effects of any of the other poisons that happen to be in the water. Okay, so that's one of the reasons that we study pH.